Hello, my name is Steve Knowles and I work for the Further Maths Support Programme in Wales. If there are any comments or issues that you feel you would like further clarification on during this presentation, then you can contact me on either of the two email addresses that you can see on the screen on the first slide. Now, this particular session is going to be on pure mathematics, and we're actually going to look at 4 topics, 3 of which will come up during the A2 modules, and the 4th one is more of an interest within the pure mathematics. Now, the first topic is going to be further trigonometry. And with regard to that, we actually start with a definition. Now, the definition is that t is equal to tan half of x. Now, as with all things in mathematics, if it's at all possible, we go back to the DAD system. Draw a diagram. DAD. Draw a diagram. What does it look like? Now, if we do that, as you can see, we end up with the angle, as you can see in the bottom left. It's a right angle triangle, and from the work that you did back in year 10 on trigonometry, tan is opposite over adjacent. Well, if we say that tan of half x is t, that means that the opposite side is of length t and the adjacent side is of length 1. Now, to that end, I can complete the triangle and find the length of the hypotenuse. Now, if that's the right angle, then the hypotenuse is going to be the square root of 1 plus t squared. And that is your basic Pythagoras theorem that you did back in year 8, year 9. Now, once you've got that, we are then in a position to find the values of sine of half x. So sine of half x, sine half x is opposite t divided by hypotenuse 1 plus t squared. And then we can do a similar thing for cos half x. I should really put brackets around these. Makes it a bit clearer. And that equals 1 over 1 plus t squared. Square root of 1 plus t squared. Don't forget the squared. So we can do that, and that's based on work that we've done in year 8, year 9, year 10, the Pythagoras theorem and the trigonometry. So we can build that picture up. Now, once we've got there, what we need to find really are what are the values of sine of x, not half x, but sine of x, cos of x, and tan of x. So that's what we're going to be doing, is we're going to be looking for sine x, cos x, and tan x, and we're going to use the double angle formula. Now, in terms of that, if we do sine x, sine of x is twice sine half x bracket in times cos of half x. And that is a formula that you will encounter from the A-level maths. Now, we've just written down the value of sine of half x and cos of half x. So that actually becomes 2 times t over 1 square root of 1 plus t squared times cos, which is 1 over square root of 1 plus t squared, which ends up as sin x equals 2t over 1 plus t squared. And there's no square root because we're multiplying the square root by itself. So squaring a square root just eliminates it. And similarly, if we do cos x from the double angle formula, cos of x equals cos squared half x minus sine squared half x. And that will give me 1 over 1 plus t squared minus t squared over 1 plus t squared. So therefore cos x is equal to 1 minus t squared over 1 plus t squared. So those are the first two, the sin x and the cos x. Now, when it comes to the tan x, what we have there is that tan x, from the work that you've done in Unit 1 of the A-level mathematics, you know that tan of x equals sine of x divided by cos of x. So that is actually twice sine half x times cos of half x divided by cos squared of half x minus the sine squared. So that's what it's actually worth. But then we just say to ourselves, but hold on a moment, didn't I just work these out? So what we've got is, we can either substitute what we've just worked out, which is 2t over 1 plus t squared, pop the bracket around that. Now we're dividing by another fraction, so that's the same as multiplying by the reciprocal of that fraction. So it's times 1 plus t squared brackets divided by 1 minus t squared. Again, I'll put that in brackets as well. So what we can say is that the 1 plus t squared down here cancels with the 1 plus t squared up there. So that in turn will leave us with tan of x is equal to 2t over 1 minus t squared. Now, in its own right, this is just a nice way of saying, look, I know these formulae, I can use them, I can manipulate, I can remember things. In terms of practical use, we can make these substitutions for sin x, cos x and tan x, and we can substitute them into an equation, and consequently we can solve that equation. It becomes a quadratic in t, and that becomes a little bit easier to solve. So it can be used, in fact, in terms of that. Now, the other thing that we need to think about is the general solution to a trig equation. Now, all too often, a calculator, when you input inverse sine of a particular value, the calculator will give you one answer. But by the very nature of trig functions, one answer isn't correct. There are more answers. Now, if we actually look at the functions, and in particular, if we actually look at the graphs of the functions, we will see the concept about it being cyclical in nature. Now, as you can see, we have there y equals sine of x. And the physicists amongst you would call that a sine wave, which is correct. But you can see that it is every 360 degrees, we are repeating the curve. Maximum value of 1, minimum value of -1. And so it fluctuates. So if I choose any number between -1 and 1 on the y-axis and draw a horizontal line, every time that horizontal line meets my sine wave, that is a solution to the equation. Now, normally the calculator gives you the closest value to 0. So if you said -0.5, it wouldn't take the value which is, and if I just do it in red, it wouldn't take you here. I would be very surprised if your calculator gave you that point there. It is more likely to give you that value there, because that one is closer to 0, or 0 degrees, I should say. So that's how the calculator works. But you can see already that if we talk about -0.5, we've got the red cross, the red circle, and we'll do it as an ampersand, and the red A. And we also have a fourth one here, we'll do it as a tick. So just between -360 and 360, we have 4 solutions when y equals -1/2. So we need to find an equation that will give us all the answers that we require as we keep going round and round the circle. And the similar process can be applied to the cosine of x. Now that's a cosine curve. As you can see, that one has line symmetry about 0 degrees. The sine wave has rotational symmetry about 0 degrees. Slight difference between the two. There's what they call a 90-degree phase shift between the two, between sine and cosine. Again, with this one, if we choose the value at plus 0.5, we have one solution. If I just number it 1, another one there 2, another one there 3, and another one there, 4. So I need to be thinking about how do I come up with this equation? And again, similar process. If we look at tangent, we have those. So if we take plus 1, we've got between minus 360 and plus 360, we've got 1 answer, 2 answers, 3 answers, 4 answers, and that's it. This answer here on the end with a circle on it is outside the 360-degree range. So we've got a repetition of answers, and we need a way of finding all of these answers. Now, if we take a slightly different diagram, you can see from this one that as you move around the circle, so you move up and down the sine wave. So that we've got different answers. So that, but you can also see that if we track this one back, that this angle here from there round to there is the same numerical value as that answer. Those two give you the same. Now, one of the things that you learned when you were solving trig equations in Mathematics Unit 1 was about all angles are measured from the horizontal. So they're either measured from 0, which is in the positive x direction, or they're measured from the 180 in the negative x direction. All your angles are measured in that system, in that way. Now, to that end, you also learnt that you had the system, I tend to call it, or I've learned it as all silver teacups. I start in quadrant 1, which is the top right. I then move anti-clockwise into quadrant 2, continue moving anti-clockwise into quadrant 3, and I finish in quadrant 4. Now I know some staff teach it as cast, but why are we starting in the last quadrant and not the first quadrant? We start where they are all positive. So all, S for silver, which is also S for sine, T for tea, which is T for tan, and C for cups, which is C for cosine. So if you have a positive angle, or a positive value on an angle for sine, you know that it's either going to be 0 plus something to pull you into quadrant 1, or it's going to be 180 minus something to pull you into quadrant 2. So that's what we're working on. We're working from this diagram. How do I put myself into that particular quadrant? So that's where it all comes from. Now, if you take, for example, these 3 questions, you've got sine x equals a half, cos x equals a half, and tan x equals 1. So over the next 3 slides, I'm going to actually come up with the generic formula for each one of these, sine, cos, and tan. Now, in terms of that, what we've got is that we've got sine x equals a half. So we pop it up here. Sine x equals a half. So that will give me that x equals sine to the minus 1 of a half. And your calculator will very, very kindly throw out that you've got 30 degrees, or pi by 6, depending on how you've set up your calculator. Now again, if we come to our all silver teacups diagram, we've got that is 30 degrees. Now I've said everything hinges on where you are in relation to the horizontal. All angles are positive in quadrant 1, top right. Sine is positive in quadrant 2, top left. So I need to put my angle back in here. So I need to go back in there 30 degrees. So my second answer, if we start from 0, is going to be 150 degrees. And then my next answer is going to be on the next loop around the circle. So it's going to be 390. And then it's going to be 510. They should all be in degrees. Oops. Comma, dot, 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 dot. So dots indicating there are more answers. We've only found those. Now we want the general solution. Now the general solution for sine is as follows. Now what we've got is we've got x equals, now I'm going to write it this way, 30 degrees times, and then in brackets, minus 1 to the power of n. So think about it this way. When n is 0, minus 1 to the power of 0 is 30. Perfect. That's what I want. But when n is 1, we've got minus 1 to the power of 1, which is minus 1, multiplied by 30 gives me minus 30. But I need to add on 180 degrees. So I'm going to put there plus 180 degrees. Now the problem is, if I leave it like that, let's go back and do when n is 0. When n is 0, we've got 30 degrees plus 180, 210. Oh, that's not correct. I need to make that 180 disappear when n is 0. The simple option is I multiply by n. So when n is 0, we've got 30 plus nothing. When n is 1, we have minus 30 plus 180 gives the 150. When n is 2, we've got 30 plus 360 gives the 390. So that is the general solution for sine. Now that's obviously quite a tricky one in terms of the minus 1 to the power of n. So you need to go away and just look at that. You will meet this again. You will be taught this again. But it's just nice to have a look at it and see exactly where everything comes from. So if we move on and then look at the next one, which was cos x equals a half. So now we've got cos x equals a half. I've tried to pick the numbers so that they're relatively straightforward I didn't really want to pick awkward decimals to give me awkward angles, so I've tried to pick values that will give me nice, easy angles to work with. Because at the moment, we don't want to be worrying about the angles, we want to be thinking more about the process as to how we put it together. Now, from there, we have that x equals cos to the minus 1 over half. So therefore, x equals 60 degrees. That's my first answer. Now again, there, all takes me up here. So it comes round that way, 60 degrees. So everything's positive there, cosine's positive, so it has to be 60 degrees. Second quadrant, it's only sine, no answer there. Third quadrant, only tangent, it's not there. Fourth quadrant, cosine. So it comes down 60 degrees. So we start off at 0 when we're facing in the positive x direction. Our first answer is 60. The next one is 60 degrees before I complete the circle. So that's going to be 300 degrees. My next answer is going to be 420. Full circle, 360 plus the 60. And then the next one is going to be a full circle, 360 plus the original 300. So it's going to be 660. Over dot, 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 dot. There you go, 4 dots. So as you can see here, we're looking at 0 or 360 plus or minus the angle that's closest to 0. Well, the angle that's closest to 0 is 60 degrees, so it's going to be 0 plus 60 or 360 minus 60. Or then it's going, the next answer is 360 plus 60. So we always work on that. Now, the general solution is as follows. X equals, now it's going to be 360 degrees multiplied by n. And it's going to be then plus or minus 60 degrees. So when n is 0, it's 360 times 0 plus 60. When n is 1, it's 360 minus 60 is 300, and then 360 plus 60 is 420. Then you do n is 2. So apart from the first one, we plus and minus 60 from every subsequent one, because we don't really want to start at minus 60 degrees. So that's the value of cosine. Now, when we then look at tangent, again, I've tried to choose a reasonably sensible question. We've got that tan x, do it right, red, thank you. So tan x equals 1. So that gives me that x equals tan to the minus 1 of 1. As I say, I've picked nice easy numbers, so that means that x is 45 degrees. Now, we again go back to our all silver teacups. 45 is up there. Now, all angles are positive there, so we want 45 degrees. Second quadrant, only sine. That's no good to me at all. The next quadrant, tangent is positive. So when we've got +1, tangent could be there. So it comes down that way, and that's at 45 degrees also. So effectively, it's just going straight through the origin. So the next angle is going to be 180 plus 45, which is 225. The next angle is going to be 2 lots of 180, 360, plus 45, 405. The next angle is going to be 3 lots of 180, 540, plus 45. So it's 585 degrees, comma, 1, 2, 3, 4. Again, continues, goes on and on and on. So our general solution is as follows. X equals, in this case, it's 45 degrees. Now, obviously, if we're looking at a very generic one, we would replace 45 with theta or alpha, but just some angle. And then it's going to be plus n lots of pi, or 180 degrees. Do it as, keep it all in degrees. (180 degrees). So when n is 0, it's 0 plus 45. When n is 1, it's 180 plus 45, which is 225. When n is 2, it's 360 plus 45, and so on. So it's just continually going round and round in that circle. And that is an important thing, that sometimes we limit ourselves in our solutions when we should be thinking there's more than one solution. And in one sense, perhaps this ties in with the concept of proof. The proof is for every single number, this general solution is now for every single lap or every single circle that we go around. So that's just a flavour of the further trigonometry that you'll be looking at, and some of the concepts and ideas that you'll get to meet and look at in further depth. Now, those are trigonometric functions. In year 13, for further maths, you will also study hyperbolic functions. Now, they are specific functions, but they follow very closely alongside the trig functions. And there are one or two little twists and turns when you're studying hyperbolic functions that you really do need to be careful over. So the first thing we need to do is to name the 3 functions. Now there should be an equivalent sine, cosine and tangent, but we can't use sine, cosine, tangent because they're for trig functions and these are hyperbolic functions. Similarly, where we've got sec, cosec and cot, there will be those functions also with hyperbolic functions. But if we stick with the 3 basic ones, now the 3 basic ones are there. It's SINH, which I tend to pronounce as shine. Now the reason for that then is there's no overlap or no doubting. When I say shine, I know I'm talking about hyperbolic functions and not trig functions. And I'm not keen on saying sine H, because you might think that H is the angle. So I call it shine. The second one, I literally say it as it is, cosh. So that's cosh x. And the last one, I pronounce it as tanch. Now, other people will pronounce it in different ways, so obviously you need to clear that up with whoever's teaching you. But please make sure that whichever way you pronounce it, you do not mix it up with the trig functions. And I cannot stress that enough. Now, the thing about hyperbolic functions is that they are effectively defined using the exponential function. Now, these are the definitions of sine, cosh, and tanch. Sine is e to the power of x minus e to the minus x, all divided by 2. Cosh is e to the x plus e to the minus x divided by 2. And tanch is sine divided by cosh, so that's why it's e to the x minus e to the minus x divided by e to the x plus e to the minus x. Now the two graphs of e to the x and e to the minus x, neither of them, if I just draw them here, and I'll do them in different colours, and it passes through the point 1, and that's e to the x. I'm not going to put y equals. And then we'll do the other one in, let's pick a nice shade. Let's try melon yellow. This one comes down this way. And there. Art was never my strong point. E to the minus x. So there we are. We've got that. Now, those are the two curves. So we're either adding them to get cosh, and when we add them, we divide by 2. So I will put copies of the graphs up, but that's where they come from. They come from those two graphs. Now, in terms of that, if we actually look at the three graphs individually, the graph of sine is almost like a cubic. Obviously, because we've got huge numbers there, that's why it looks flat for such a long region. But it's almost, as I say, it's almost a cubic graph. If you think about it in terms of a cubic, then you won't go far wrong when you're sketching sine of x. As you can see, when you get to 10, the graph almost goes vertical. So again, showing that e to the power of x gets very big very quickly once you start getting sort of even semi-large numbers put into it. Now the next one, which is cosh x, is a very, very interesting curve indeed. And a lot of people say, well, no, it can't be an interesting curve, it's just mathematics. That shape there, as you can see, it goes through the point 1. It's not quite U-shaped. It is a little bit flatter, but this curve has a special name. This curve is known by the name of catenary. C-A-T-E-N-A-R-Y. Now, that curve is very, very important in engineering and building. And if, for example, you all wanted to construct your own version of a catenary, it is very, very simple to do. Now, obviously, it all depends on the values of x that you take and whether you zoom in on the picture or you zoom out. But if you have, for example, a metal necklace, not one of these leather ones, but a metal necklace. If you unclip the necklace and hold the two ends, the shape that the metal necklace makes between your two hands is a catenary. Other examples of where you will see a catenary will be that if you have a ship at anchor, the metal coming down will be in part of a catenary. Another example of where you will see a catenary is on suspension bridges with the cables there. So again, this is why it's got its own special name, is the fact that it's used so much within engineering, and it's just an important curve. Now the last one obviously is the tangent curve, and that is almost like a tan curve, except it's going horizontal, but it's going between -1 and 1. But the shape is almost sort of back to front. If you rotate it, it's almost a back to front tan curve. Again, that one they tend not to ask very often. They usually ask you to sketch the cosh curve, but the tangent curve not so much. So it might be worth practicing just in case this is the odd year that they do actually ask you for it. Now, obviously, because we're dealing with hyperbolic functions, which are almost an offshoot of trig functions, then we can actually differentiate the hyperbolic functions. But what I'm going to do is I'm going to show you, rather than just say, right, if y equals sine x, what is dy dx? I will show you how I get that answer. And again, they are closely linked to the trig functions, but there are one or two little twists, so we need to be careful. Now, if you've got the first one, y equals sine x, then that gives you that y equals e to the x minus e to the minus x all over 2. 2 is a constant, so technically when we differentiate, we're only going to differentiate the numerator, and we're just going to copy down the denominator. So dy by dx now, in terms of differentiating exponentials, this is one of the things that you will come across in Unit 3 of the Mathematics A level. So in other words, when you start year 13. Now, the actual rule for differentiating an exponential is that it is exactly the same. You differentiate e to the x, you get e to the x. And then copy down the minus symbol in the middle, and then I'm going to put a brackets. Differentiate e to the power of minus x gives me e to the power of minus x. And then we step inside that and we say, right, let's differentiate the power. Let's differentiate minus x. Well, if we differentiate minus x, we get minus 1. That's all divided by 2. So that is, in effect, e to the x plus e to the minus x divided by 2. So therefore, dy by dx is equal to cosh x. Now, in one sense, if you think to yourself, right, when I was doing trigonometry, when I differentiate y equals sine x, I get dy dx equals cos x. So this one basically is almost like saying, well, even though you put the h on the end, it doesn't matter, we've still got the same thing. That isn't always the case. We need to be very, very careful as we go through. So when we look at the next one, which is cos x, we have there that if we've got that, that equals e to the x plus e to the minus x, all divided by 2. So dy by dx is, well, differentiate e to the x gives you e to the x. Copy down the plus symbol in the middle, open up my brackets, differentiate e to the minus x gives me e to the minus x. Close my brackets. But then we step and we differentiate the power. We've differentiated the e part and we just copy it down. We then step inside the e part and differentiate the power and we get minus 1. That's all over 2 because we do nothing with the 2, we just copy it down. So that will give me e to the x minus e to the minus x divided by 2. So therefore, dy by dx equals sin x. That's the difference. When you did trigonometry, if you had y equals cos x, dy dx equals minus sine x. But with hyperbolic functions, when you differentiate cos, you get sine. You get the positive value. So what we've got then, moving on to tanh. Now, obviously, tanh takes a little bit more time because it's got the fraction, and we need to be able to deal with the fraction. So we've got this. This is e to the x minus e to the minus x divided by e to the x plus e to the minus x. Now technically you've got two functions, and I'm going to call them function u on the top and function v on the bottom, rather than f and g. It's a bit too close to e. I'm getting a bit twitchy there, so I want to keep it as far away from that as possible. So I've got my two functions. Now because it's a fraction, another name for a fraction is a quotient. One of the things that you learn in year 13 for the A-level maths unit 3 is a thing called the quotient rule. That if you're given a fraction like this, there is a rule to help you to make it that little bit quicker and that little bit easier for you to work with. Now the rule is, if that's my function, then dy by dx, if that's my function y, so y equals, then dy by dx is equal to, I copy down the v function and I multiply it by the differential of the u function. And this is the sneaky bit. We then subtract, copy down the u function and multiply by the dv function. And that's all divided by v squared. Now, that particular formula is a set formula, and might be worthwhile trying to learn it, but it is very, very important. You need to be able to use the quotient rule. Now, if we do that, what we have when we differentiate, that's a y function, so dy by dx, so dy by dx equals, we copy down the v function, which is e to the power of x plus e to the power of minus x. And we multiply it by the differential of the u function, the top, which is e to the x plus e to the minus x. And again, I refer you to the work that we did when we differentiated sine and cosh earlier, and we differentiated either e to the x minus e to the minus x, or the other one. And then we subtract, because that's what it says in the formula, the top function, the u, which is e to the x minus e to the minus x, and we multiply that by the differential of the bottom, which is e to the x minus e to the minus x. And all of that is divided by e to the x plus e to the minus x squared. That's what it says in the formula. Now at the moment, I am not going to work out the denominator. I am not going to expand the brackets. My attention is totally focused on the numerator. So expanding the first two brackets will give me e to the 2x then plus 2, because we're multiplying e to the power of x times e to the power of minus x. And your basic work that you did in year 12 on indices, you add the powers. Well, x take away x is 0, e to the power of 0 is 1, and because we're squaring, there's a 2 in the middle. And then plus e to the minus 2x. And then we've got minus e to the 2x plus 2 minus e to the minus 2x. And that's all divided by e to the x plus e to the minus x and then that's going to be all squared. So top line I can simplify because I've got e to the 2x, take away e to the 2x. I've got e to the minus 2x, take away e to the minus 2x. So when we go to the next slide, we can finish this off. That will give me a total of So equals, it'll give me 4 over e to the x plus e to the minus x squared. We'll get there and put all the lines in, and that is the same as 2 over e to the x plus e to the minus x all squared. Now, that is actually 1 over cos x all squared, which is 1 over cos squared x, and 1 over cos squared is, it's almost like sec, but again we put a h on the end to indicate it's hyperbolic, and that becomes, and I pronounce it sesh squared x. Now, if we take as an example, if we've got y equals, let's really push the boat out here, tanh of 11x, using what we have just above, then we know that dy by dx is going to be sesh squared of 11x. But the other thing we do is we go inside the bracket and we differentiate 11x and we get 11. So the differentiation is a two-parter. We differentiate the hyperbolic function and it gives whatever it gives us. But then we go inside this bracket and we differentiate the function of x, just as if we were back in year 12 doing unit 1, differentiation of a polynomial. We differentiate 11x and we get 11. That gets stuck on the outside. So again, we need to just have a little look at how we did what we did with the trig functions, and then we just almost carry it on into the hyperbolic functions. But it's a good guide and a good aid for us moving on. Now, there are some questions for you to try, and again, if you want to try them and submit the results to me, differentiate those 3. But again, with each one, as I said, if you think about it and you say, right, I'm going to put a bracket in there. For each one, we differentiate the hyperbolic function. So differentiate sine, what does it give? And then we write down cos of whatever. And then we go inside that red bracket. We say, well, okay, let's differentiate 3x. And whatever value we get there gets put in front of our hyperbolic function. And it's just literally that all the time. Now, as with ordinary trig functions, where you can have inverse functions, we can also have inverse functions for the hyperbolic functions. So again, look at how we actually set this up. So if we've got, say for example, y equals sine to the -1 of x. So if we actually go through that, now if you think about when you've done this in the past and you've looked at rearranging that, you want to get an expression so that you replace the x with the y and the y with the x. Now with this one, what you're going to do first is you're going to say that sin y equals x. That's going to be our first step. We don't really want to work with inverse functions, but sin y is actually e to the y minus e to the minus y divided by 2, and that still equals x. So double both sides because I don't like working with fractions, so let's get rid of it. E to the y minus e to the minus y equals 2x. I've got positive and negative powers. I'm not really too fussed about that. So what I'm going to do is I'm going to multiply throughout by e to the power of y. So that will give me e to the power of 2y minus 1 equals 2x e to the power of y. Take the 2x over, and that will give me e to the power of 2y minus 2x e to the power of y minus 1 equals 0. Now instead of having x squared x number equals 0, as you were so used to doing at GCSE, we now have a quadratic in e to the power of y. I don't know whether that will factorize or not, so I'm not going to risk it. We're going to say that a equals 1, b equals minus 2x, and c equals 1. Now, substitute those into the formula. So that will give me, so again, we're carrying on with sin to the minus 1 of x. E to the power of y equals minus b, so 2x, plus or minus square root. B squared is going to be 4x squared minus 4 times a times c. So that's going to work out as plus 1, plus 4, because it's plus 1 and minus 1. And that's all divided by 2. So e to the y equals, I'm going to divide by 2. So 2 goes into 2x, just to leave x, plus or minus. When the 2 goes inside the square root symbol, it becomes 4. So that will leave me with the square root of x squared plus 1. So that means then that y is equal to log of x plus the square root of x squared plus 1. Now, the reason it's plus and I've dropped the minus is the fact that we cannot have x minus x squared plus 1 square rooted, because x squared plus 1 is going to be bigger than x is greater than x. And if we take big number from a small number, we end up with a negative number. Think back to what does a log curve look like. You cannot take the log of a negative number. So that's why we don't have the minus part. That's why it looks as if I've just said, I can't be bothered to write it down. It isn't that I can't be bothered. I've thought it through and I've applied logic and knowledge that I've gained previously. What does a log graph look like? I cannot take the log of a negative number, so therefore I can't have that as part of my solution. So following on from that, we've said y is log of da 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 da, but we've also said at the top of the slide that y is sine to the minus 1 of x. So therefore, sine to the minus 1 of x put that in brackets, equals log of x plus x squared plus 1. Square rooted. There you go. So it's that. So that's what inverse sine is. And again, we can do all sorts with it and we can work with it within questions and so on. So hopefully that it will make it a little bit easier as to what we actually need. Now, with the other two, you've obviously got cosh as the next one. Again, trying to do the same as we do with sine, cos, tan. It's sine, cosh, tanch. So we work in that way. Go through the same process. Cosh of y equals x. So e to the power of y plus e to the minus y divided by 2 equals x. Now, what I'm going to do is I'm going to leave you fill that bit in, and I'm going to go towards the end. So see if you can fill in the gaps. And again, if there's any problems, you have my email address. Please contact me and I will go through bits with you. So if we move towards the end, we have the following. So coming all the way down, we end up with e to the power of y is equal to x plus or minus, and in this case it's the square root of x squared minus 1. Now in this case, both are the solution, because if I have x squared and take the square root of it, I get back to x. So if I have x squared take away 1 and I take the square root, I will get a number that is just slightly smaller than x, so that when I take that away from x, I'm still going to be left with a positive number. Yes, it's going to be a small number, but it's still a positive number. So that's I am allowed to do. So I've got my two solutions. that y is log of x plus or minus the square root of x squared minus 1. It has both parts. So that's where we're coming from there. So it ends up as, we end up with, going down a few more stages, that we end up with that we have y equals plus or minus the log of x plus the square root of x squared minus 1. And again, I will go through that with anybody that wishes to write in. Now, the Tanch version is slightly different. Here we start again with Tanch of y equals x. So that is e to the y minus e to the minus y divided by e to the y plus e to the minus y, and that all equals x. The fraction, let's get rid of the fraction. So that gives me e to the y minus e to the minus y equals x e to the y plus x e to the minus y. Multiply throughout by e to the power of y. E to the 2y minus 1 equals x e to the 2y plus x. Separate out the e to the y part from the rest. E to the 2y, open brackets, 1 minus x equals 1 plus x. So that gives us that. And then that will give us that e to the 2y equals 1 plus x over 1 minus x. So 2y equals log of 1 plus x over 1 minus x. And so y equals a half log 1 plus x over 1 minus x. So technically we have that inverse tan tanch minus 1 of x equals a half log 1 plus x over 1 minus x. And there it is. So again, time consuming to go through those, but it's always nice to see where they've come from. Occasionally that you'll be given them within the formula booklet, so please check that if they're there. But it's nice to see where they come from, rather than just somebody doing a bit of magic and hey presto, there it arrives. You have actually seen, and you can see where it comes from and how it all fits together. Now, the next bit is differential equations, and you've started to look at differential equations in M3, Unit 3, FM3, and there you looked at differential equations in terms of motion in a straight line. Going into FM6, you will look at differential equations again, but this time you're looking more at circular motion, but also you need to do differential equations whilst you're working within the FM4 course as well. So this is why I want to look at it here now. Now, the big thing this part is that it's now moving into what they call a second order differential equation. And in terms of that, it takes that sort of format. The y double dash basically means d2y dx squared plus a dy dx plus by equals some function of x. Now that function of x will effectively tell me how my solution is going to look when it is finished. Now, in terms of that, the actual solution is made up of two parts. We initially start to consider that f of x equals 0. Now that is, when we solve that, that gives us what is known as a complementary function. And then we start to look at what value or what expression have they given us for f of x. And then we put in a solution based on the value of f of x that they've given us. So the solution is split into these two parts, the complementary function and then the particular integral. And a lot of it is just about substitution. Now, if you look at the complementary function that's there in front of you, that's almost like looking at a quadratic equation. Y double dash, y dash, y to the no dash. And we need to think about how am I going to turn this function, y double dash plus a y dash plus by equals 0, into a quadratic. Now, the way in which you do that is by making a simple substitution, and that substitution is y equals e to the power of mx. We make that substitution and we will substitute it into our original equation, and then we look at it and hopefully we will get the quadratic equation, and then it will make a lot of sense as to exactly what we're doing. Now, to that end, I've got some questions. There's the first one. Now, I've said to you that we're going to make the substitution y equals e to the mx. So if y equals e to the mx, then y dash is differentiate the exponential function, and as I said, you get the exponential function. There is no change. We just get that. Mx, e to the mx. We then ignore the exponential part, we focus on the mx, and we differentiate that. Whatever we get is put in front of the exponential. So when we differentiate mx, we literally get m. And then we differentiate the second time. So y double dash equals, differentiate the exponential, we've got e to the mx, and then we've got our original m from the first differential, but now we're differentiating again. So we have to multiply by m again. So it's m squared. So we substitute those three parts into our equation, and we will end up with m squared e to the mx plus 5m e to the mx plus 6e to the mx, and that equals 0. I can take out the common factor of e to the power of mx, and I'm left then with m squared plus 5m plus 6, and that equals 0. So I'm multiplying two numbers together and I get the answer 0. Oh, this takes me back to year 10 when I was solving quadratics. And I factorised my quadratics, and I was told that in my two brackets in year 10, I did the first bracket, the first number was 0, or the second number was 0. Well, e to the power of mx can never be 0. So, as e to the mx cannot equal 0, or does not equal 0, this implies that m squared plus 5m plus 6 equals 0. So that's what we need to solve. So effectively we're now saying, right, let's go back to year 10 work and let's solve a quadratic. So here you are doing FM4 and you're using year 10 work. So we are lucky that that will actually factorize into m plus 2 and m plus 3. Equal to 0. So this implies that from the first bracket, m equals minus 2, and from the second bracket, or m equals minus 3. So the solution that we will write down of that first equation, y double dash plus 5y dash plus 6y equals 0, will be, so therefore, y equals some constant a times e to the power of the first m minus 2x plus another constant b times e to the power of minus 3x. So what we've done is we've put that answer up there in place of m, and we've put that answer there in place of n. So we've done it in terms of that. Now obviously, if this was a proper full question, they would need to give you some values for x and y to enable you to work out the values of a and b. Those, if you like, are our constants of integration. So we need more information to go back and work those out. But in the first instance, that is like saying plus c when you were doing integration back in year 12 in unit 1 mathematics. So that's where we are with that one. Now, as you can see, that one factorized and it was quite nice. So I had my two solutions. And if you notice, a multiplied by e to the power of the first answer, plus b e to the power of the second answer, both with x. Now, when we look at the next question, we've got that one. Now that we start in exactly the same way. Let y equals e to the mx. So we're looking for, because we're almost starting to think now, this is going to give me a quadratic. I'm going to have two values for m, so therefore m1 and m2 are going to be my two components for the answer. Now, in terms of this, that will give me y dashed equals m e to the mx, and y double dash is going to give me m squared e to the mx. Substituting that back into the original equation, m squared e to the mx minus 4m e to the mx plus 4 e to the mx equals 0. Take out the common factor of e to the mx, brackets, m squared minus 4m plus 4 equals 0. But e to the mx does not equal 0. So consequently, that will give me m squared minus 4m plus 4 equals 0. That will factorize m minus 2, m minus 2 equals 0. So therefore, m equals 2 or m equals 2. Oh, this time we've got a repeated root. They're both real numbers, but it's repeated. Consequence of this now applies to the final stage. Because we've only appears as if we've got one answer, I need to make it two. Now the way in which we do that is we say the following. Therefore, y equals, open brackets, ax plus b times e to the 2x. Notice this time we've put an x with one of the letters. I put it with the first one. I've seen some staff write it as a plus bx. Well, obviously, when you put the conditions in, the values of a and b aren't the same then as they are in this case. So, but they will work out the same. In that, if you put the x with the b, then that value of b will equal this value of a. So it's just in a different order, that's all. But that's the big difference. One of my constants of integration has the letter x to go with it. So that's where the big difference is. Now, as far as the next question is concerned, it looks as if we're just after the complementary function because it equals 0. So we start with our basic let y equals e to the mx. So y dash equals m e to the mx, and y double dash equals m squared e to the mx. So substituting that in, m squared e to the mx minus 2m e to the mx plus 3 e to the mx equals 0. Take out the common factor of e to the mx, m squared minus 2m plus 3 equals 0, but e to the mx does not equal 0. Now, you should be noticing the pattern that's coming up in the method of solution of these every single time. So, moving on to the next slide. And what we have there is we now have a quadratic, which is m squared plus 2m plus 3 equals 0. Will not factorize, so we use the formula m equals minus 2 plus or minus the square root of 4 minus 12 all divided by 2, which is minus 2 plus or minus the square root of minus 8 all divided by 2. So therefore m equals minus 1 plus or minus square root of minus 2, which is minus 1 plus or minus I root 2. So we've got a complex number. And again, how do I deal with that? And the solution to this one is as follows. We have y equals e to the minus x. So technically, if I do it in red, that value of minus 1 has gone in front of the x. That's where that has gone. What we haven't done with or dealt with is the root 2. And the fact that we've got I. Now the way around that is as follows. What we do is we write that as a cos, and then it's root 2 of x. We take the number that's with the I and we put it in front of the x in the cosine, and then we do plus b, and then we'll do sine of open brackets root 2x. And again, you'll obviously do quite a few more examples on this, but you've got a rough idea and a rough flavour of how these things work, so that you can have real distinct roots, first question, real repeated roots, question 2, and now complex roots, introduces sine and cosine. So that's where we are with the solution of the differential equations. Now, in terms of the particular integral, as I said, we need to look at the expression of f of x and substitute in the generic form of that f of x. So, if we've got this, if we've got y double dash da 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 equals x squared, we will substitute y equals a, start with the x squared and go down. So it's ax squared plus bx plus c. If it was x cubed, it would be ax cubed plus bx squared plus cx plus d. And then they give you initial conditions and you can work out what the values of a, b and c actually are. Now, as I say, the overall solution to this is literally you solve it as if it's equal to 0 and get the complementary function, and then you find the particular integral and you just literally add the two together. And that is how you get your solution for a second order differential equation. Now, that particular topic is very, very important when you get into university, into all sorts of degrees. It's used in solving a lot of problems, so it's worth understanding when you're doing FM4. If you don't understand, then you need to make sure that you go back over it and that you find out. Now, the last topic I want to look at is multiplication of vectors. Now, when you did Unit 1 Mathematics, you looked at multiplying a vector quantity by a scalar. So you had a vector and you said, right, I'm going to make it 3 times as long. I'm going to make it 4 times as long. And you just multiplied each term. In the AS4 further maths, you actually looked at what was known as the scalar product or dot product. There is also a third method, which we will come to now. So as you can see, that's what we've done. We've done the scalar quantity. We've multiplied a vector by another vector by using the dot product. And then we've used a vector times a vector, and this is the new one, by this thing called a cross product. Now, as I said, first method, Unit 1 of A-level maths, second method, FM Unit 1. So they were both at AS level. Now, the third method, it's not on the A-level syllabus anymore, but it is a simple way of finding vectors that are perpendicular to planes. It does make a lot of that work so much easier. If you've got two vectors in a plane, you can do the cross product of those two vectors and you come up with the answer that is perpendicular to both. And that's why it's so important. So as I said, the vector, plane A and B. The plane can be defined in terms of those two vectors. And that's the definition of the cross product. As you can see, it looks as if it's a multiply sign, but it's a cross product. So we've got the magnitude of A times the magnitude of B times sine theta. And then we're also multiplying by n, where n is the unit vector perpendicular to both A and B. So in the first instance, you're going, oh my goodness, this is really hard going. However, there is a way of doing it that does make it much easier for you. Now, before we just get to that, the value of AB sine theta is actually the area of the parallelogram made by the vectors A and B. So if we actually look at it, there it is, A and B. So we've got that parallelogram that is basically in grey, and if you notice, the value of n goes up the screen if we're doing A cross B, and you say it as A cross B. You do not say it as A times B. It's A cross B. But if you're doing B cross A, it goes down the street. And that is important. It's not the same. Now, this is what I was saying about earlier. The best approach to these is to use the determinant of a 3 by 3 matrix. Now, you will meet that at the beginning of FM4. How do I find the determinant of a 3 by 3 matrix? Now, we've got an example here. For this, if we're doing all of these, and then we've got I, J, K, if I just do it for the I component, and then you can see it, technically, we cross out the I column. So we cross out down there, and we cross out across the I row. Anything involving the letter I has gone. That's going to be written down. How do I get the number in front of I? Well, from your work you did on 2 by 2 matrices, you multiply those two together. Minus 1 times minus 1. So you've got minus 1 times minus 1. Let's just change colour. We'll go to a nice shade of blue. And then we're going to subtract 1 times 2. So that technically gives me 1 take away 2, which is minus 1. And that is the minus number in front of the I. So cross out the I's and work out those numbers go in front of the I. And similarly, we would cross out the J column and the J row, put the J down, and we'll do 3 times minus 1, and we work it out that way. So that's a process that you learn reasonably early on within FM4, but it is quite important. So you can see that it has a use when you're doing the cross product of vectors. Now, in one sense, we said when we were doing the dot product that I dot I gave 1. Unit vector I times the unit vector I. So modulus of 1 times the modulus of 1 times cos of 0. And cos of 0 works out to be 1. So you're saying 1 times 1 times 1 is 1. But here, I've ended up with I, J, and K in my result. So how do I decide which one gives which? Now, there is a little rule. Those are your facts. That I cross J equals K. J cross K equals I. And K cross I, oh my goodness, equals J. Now, if you do it in a cyclical fashion, you get the following. So if you start with I and you move round to J, you end up with K. J times K, you keep going round the circle, ends up with I. K times I, you end up with J. If I go in the opposite direction, you can see that I cross K gives minus J. And K cross J gives minus I. And I cross I, because it's sine of 0, because it's the modulus of this one times the modulus of itself, so 1 times sine 0. And sine 0 is 0. So that's why when you do I cross I, you end up with nothing. It doesn't give you anything. Now, one way of actually working this is what they call the right-hand rule. So that is this one. So if you imagine that your index finger is pointing along the I-axis, the middle finger is pointing along the J-axis, your thumb is pointing along the K-axis. So I cross J gives the K, and it's worth, if you like, getting a cardboard box and putting your hand on the corners and label them I, J and K and see what happens. And then see, well, instead of doing I cross K, what if I do J cross I? Oh, I'm going in, but try it on a cardboard box. It will make a lot of sense when you've got your hand in the corner and you're moving it around. Now, the other nice thing, I said earlier that if you had A cross B, it gave you the area of the parallelogram that the vectors A and B made. But we can extend this. What if we've got three vectors? And if we extend it to three vectors, and we've got A, in this case, they haven't used the cross, they've used the accent. But technically it means A cross B cross C. It gives you the volume of that shape. And it's not the area, it gives you the volume. All right, so A cross B is the base that's standing on the table. You can just about see the yellow, and then it goes in behind that other colour. So it's that bit. So that's where it comes from. So again, it's an incredibly useful thing. It's a useful tool to help you in other problems. But again, to do this, we need tools from other parts of pure maths. We need the 3x3 matrices. So you need to make sure that as you're going through each one of these sections of the work, that you fully understand it, because you're never quite sure when it's going to come back and be useful in another part of the course. And again, the more knowledge you can gain now, the better you will be as you move forward through your educational career. I'd like to thank you all for your time and your patience, and I would like to wish you every success in the future. Thank you very much, everyone.